All right, good afternoon, everybody. Trust you're having a good day so far. As we move closer to the end of the module, I'm gonna make one minor adjustment. I know I said last time that I gave you the two videos that you should have looked at. I'm just assuming that given the need to prepare for last week, that some of you may not have had the time to watch them. So I'm just going to bring forward the lesson on protection. So I'll bring that forward to today. And then we'll look at substation and integration of renewables after this topic. So we talked today about protection. As we said, power system protection fundamentals. Key here, dealing with the fundamentals. So if you are interested in going in depth, then we'll talk in semester 2. But we just want to get some basic things about protection covered. So let's jump straight in. This is a power system. What we have here highlights our power system. We have our prime movers, we have our generator, we have our circuit breaker, your transformer, and maybe I should say the wild power system. All right. There are so many things that can happen in your power system from the prime mover side. Right, your turbine. We're talking about overpower. So in other words, your mechanical input is too much, or the input to your turbine is too much, or has exceeded a particular threshold, so to speak. I know we haven't spoken about stability, but for you, for what it's worth, let's just say overpower. We have some frequency issues. Reverse power, your system, instead of generating, start motoring, you know. From your synchronous machine standpoint, a loss of field, overexcitation. These are issues that we'll have to address. And if they occur, we have to find a way to either protect that generator or protect the system. Yes. When we come to the circuit breaker, we're talking about flashover, failure of the breaker. A failure of a breaker years ago resulted in an all-island blackout. Just one breaker, one single breaker failing, and caused the entire system to collapse. So we have to be able to monitor that breaker to see whether or not, you know, given that it ought to operate, what sort of support mechanisms do we have? We're talking about open circuits. What happens if the load is somehow separated from generation? All right. There are certain things that are going to happen to the generator that we have to address. Okay, and then we come to the system itself. Of course, this generator is connected to what we refer to as an infinite bus. What if that isn't matching up anymore? Meaning, you know, have no synchronization between the generator and the external system. You know, there's just so many things that can happen. Now, why then, or at the core, why is it important for us to have this the protection system or protection scheme, as we will speak to later on? All of these abnormalities, what really drives us? Remember, we said at the beginning that the purpose of your power system is to provide reliable power. We want to, provide reliable power to our customers. Now, that reliability also means that, I should say also, means that when persons want power, they should have it. They don't need to be consulting with the utility company. They want power when they need it, of the correct voltage, of the correct frequency, etc., etc. So part of the reason for having your protection on the system is one, that it identifies abnormalities. So it quickly identifies abnormalities and then it quickly isolates. No. Part of the reason for quick isolation is that given the need to provide a reliable power supply, it means that I can't afford to have equipment or important equipment being damaged. So one of the most protected piece of equipment in a power system is your generator, because generators, not only are they expensive, but in terms of replacement, that is a major, major, major undertaking. For those, you would have seen the news with what happened to the powerhouse at Jamalco. That's going to put their production out for years. Not months, years, a couple of years. And so one wants to really monitor the operation of the generator. And so, whether it is you are sensing abnormal vibration of your generator, there may be a problem with the shaft, which would be causing that. The generator is just, highly protected. So we'll prefer to remove it from the system, see what is happening, and then get it back into the system as quickly as possible. So it will be much cheaper for us to protect it, to look at all its operational features and protect against abnormalities where those features are concerned, rather than having to replace it. So part of protection, or part of the challenge in protection, is that in order for you to effectively protect or to put in a protection system, you have to understand the system. You have to have an in-depth understanding of the operation of the system. And as I said, that's the real challenge. And that's where students find protection a little challenging. So the protection, as I said, quick isolation. So you have to make millisecond decisions. And you have to be able to separate the system from, the faulted system. You have to separate that from the rest of the system as quickly as possible. And I say from the rest of the system because you want to be able to cause the rest of the system to continue operating. And the best way to appreciate this primary function of your power system is to consider your own breaker system at home, where you have a main breaker, and then you have several breakers that are sub-circuits controlling different plugs or lighting circuits. The question is, if you end up with a fault, let's say you're plugging a faulty iron in the kitchen or wherever you do your ironing. Let's say you plugged in a faulty iron. You would not want that your living room breaker, the breaker to your bedroom, all trip at the same time. You want just that single circuit that is controlling the kitchen to trip. Same thing with the power system. It's no different, the same concept. So if I have a problem with one generator I want to be able to isolate that generator, yes, while the rest of the system operates. If I have a problem with a transformer, I want to be able to take that transformer out without shutting down the rest of the system. Now, coming back to your to home, let us say that the breaker that's controlling the kitchen does not operate. Then it means that the fault would no longer be just localized to that circuit. It now becomes a fault for the entire panel. And so your main breaker may trip. Now, if your main breaker trips, what that will result in is that power will be lost for the entire house. All right? Now, the same is true for your power system. If you're unable to isolate, I see we come talking about the problem areas, yes? So we either isolate the equipment that is under fault, or we isolate the area that is under fault. So we are either going to isolate the kitchen, or we are going to isolate the kitchen circuits, yes? Now, if that breaker is faulty and doesn't trip, and the whole house goes, in the same way, if I am unable to isolate the faulted section or equipment in my power system, it is going to cause the fault to what we refer to as escalate. So it's going to take out more or a larger area than need be. So you can have a problem on a single transformer. And if the breaker associated with that transformer doesn't operate, then instead of taking out a single circuit, it may take out the entire substation. So you'll move from power being lost to a few hundred customers to a few thousand customers. All right? So keep that in the back of your mind as we continue the discussion on protection. Any comments, questions so far? All right. Yes, so the protection system, firstly, wishes to minimize the duration of the abnormal activity. Because the longer the fault exists, the longer the fault stays on the system, it's the higher the potential damage that can occur. So the key of quick isolation, very, very important, right? So the system wishes to minimize the duration of the abnormal activity. In other words, it's going to limit the amount of damage that will take place. And of course, if you can isolate equipment before they get damaged, then it means that you'll be able to put the system back into operation in a shorter possible time. So if you have a transformer that's overheating, if you are not able to detect and isolate that transformer, you may end up with that transformer creating a fire, which then disrupts the operation of an entire substation. So whereas you could have tripped just that circuit, and having tripped it, you may be able to transfer the entire load on a second transformer, or in a couple of days, you may be able to replace that transformer or bring in a portable transformer. Yes, then problem is solved, at least temporarily, but you would have reduced the outage time. So again, I know I'm spending a lot of time on this, but it is important that you appreciate this. The critical feature associated with the protection system is to isolate quickly, which reduces damage, reduces outage time. All right? All right, now, in terms of your protection system, there are four what I call stages, right? And in achieving or in executing these 4 stages, we use what we call protective and switchgear. And I'll speak a little more to the distinction, but your switchgear is simply your circuit breaker. The protective gear is everything else, your relays, your CTs, etc. All right? But let's focus now on the four stages. The first stage that we have to contend with is that we need to be able to detect the abnormal condition. The breakers that we have at home, they detect an abnormal condition using heat. They are thermal breakers, yes? So if the current that is passing through them exceeds a certain value, then the heat produced would cause your breakers to trip. All right? So we have to be able to detect. So first we detect. Next, we want to process the information. So the processing will have to have some intelligence. You know, whether it's a biometallic strip, whether it is as simple as a biometallic strip, whether it is static relay, or you name it, electromagnetic relay, you name it. But we have to process it. We detect, but we have to process. We have to ensure that what is being conveyed in terms of information is accurate, because you want to be sure that the action taken is based on credible or solid information. So we process the information. And then the third step is that there is initiation of isolation. So now the relay will tell the breaker to trip. So it initiates isolation. It tells the breaker what to do. Now I have there or other relevant action, because there are some cases where instead of isolation, what is triggered is an alarm. So you may get an alarm from a transformer, for example. There are certain relays that instead of tripping the transformer, what it will do is to send an alarm to your control, your central control. They will see the alarm, they will know that, okay, there's some deterioration taking place, and they will have time to react, all right? So we can either initiate isolation or we can send an alarm signal. And then finally, isolation. So we detect, process, initiate some form of action, whether isolation or an alarm, and then finally, isolation takes place. So these are the 4 stages. And what we'll be doing is we'll be looking at the equipment involved in each of these stages. So we'll be looking at the equipment that is going to help you detect that there's a fault, that there's a problem. We'll be looking at the equipment that helps you to process the information. So we process it, and then based on what comes in and based on the output of that processing, it says trip or it ignores it. And then finally, we have isolation. All right. Pause again. Any questions?
Sir, I want to ask a question.
Yes, Mr. Clark.
You mentioned that they just reference to the house breakers that use heat to cause the breaker to trip. So in case of there's a fault in one of the circuits, if it's heat that causes the breaker to trip, are you saying that it will take time for that breaker to trip?
Yes,
and
it
not
will.
trip instantaneously?
It will. It does take time.
Okay, so if the fault is instant, like a short circuit, wouldn't it trip instantly?
Well, what you would consider instantly, all right, think of it this way. Your breaker is rated at 50. Most of our host sub-circuits are 15 or 20 amps, yeah? Yes?
Yes, sir, yes.
All right. Now, if you were to run any sub-circuit in your home at full load or near full load, and go and touch the wire on that sub-circuit, you're going to feel it being quite warm. It's going to be warm. However, a short circuit, and I mean, I don't want to, well, this may be making it more significant than it really is. But if you remember, if you cast your minds back to, I know it's a sour topic now, but anyway, cast your minds back to your mid-sets. The per unit current that you would have calculated was 8 or 10 times your load current. The per unit current was 10 something, 10 point something, all right? So I want you to know, think about that multiplier in terms of what the regular house breaker would be seeing. Do you understand where I'm going with this? So if 15 amps is going to make it warm, you have 15 amps, you know, close to its rating. If you run that continuously, and you find that being warm, think of what 10 times would do.
No, I understand, sir. The next question I'm going to ask, is what would cause that fault to exceed what the breaker can manage to go to the main breaker? Then what would cause that fault to do that?
So you can have, for example, one of the things that we will talk about that impacts protection system is what we refer to as deterioration. You have had houses that have been built 10, 15, 20 years ago, and not one of the breakers have ever tripped. Neither have they been turned on or off. I mean, off, right? So they're just there, sitting down. Over time, it can deteriorate. So even in the event, I mean, I know some of you guys are in the field, and you would have gone into some areas where persons have never had reason to even look in their panel, right? But when you go in there, you find all sorts of stuff, from lizard, eggs, you name it, all right? Which means that obviously, if the lizard can get in there and have a beautiful life, then the possibility of moisture can get in. So you can have that breaker in terms of the spring mechanism for tripping, becoming corroded over time. So when you have a fault, for whatever reason, it simply will not trip. Now, the breaker, each circuit is linked back to the main breaker, because the main breaker controls the two, I mean, since we're dealing with 240 systems, controls the two main bus bars. So each breaker is linked back to the main breaker. So if the sub-circuit does not trip, it means that the fault will be escalated to becoming a main breaker fault.
Okay, so I understand.
All right? So
yes,
in the power system, and the DC I'm talking about is one that occurred at Tredegar, where a rotting pole fell. The breaker should have tripped. It didn't. Why? Because the person who was responsible for maintenance did not do his job. And every time I tell this story, I feel kind of bad, because, I mean, he's a UTech student who had that responsibility. but he didn't maintain the breaker, and the breaker simply didn't operate. And it escalated and came back into the unit. And before we know it, the entire island was out. All right. So you are going to have escalation if the local or the prescribed protection system doesn't operate. All right. Good question anyway. Okay. So in terms of the detection, so we're going to now look at these 4 areas quickly. All right. And as I said, we're looking at the equipment that are associated. So with detection, right, we're talking about current transformers, voltage transformers, your lightning arresters, and of course your relays. Now I have relays here as part of the detection, but relays are also part of the processing, and you know we look at that in a little more detail. But for your CT, it is simply looking at the current passing through, and the CT would normally operate by giving a scaled replica of whatever current is on the system. So if the current goes above a certain threshold, yes, which would have been established in the relay, then that increased current will be passed to the relay. So detection here, we're detecting currents going beyond certain values. Your voltage transformers, yeah, part of the detection mechanism. And again, you know, the exciting part, I mean, I suppose for those who have been doing their homework, they know that I am most excited about protection. You know, power systems is nice, but protection for me is where it's at. All right, so you have your voltage transformers, you have your lightning arresters. Now your lightning arresters, they do more than just detect. Because yes, they detect the lightning, but they also process and isolate. Okay, so, but we're sticking them here because yes, they're part of, they detect. Yeah? And then of course your relays need to, are used to determine or to detect whether or not the current that it is receiving or the voltage that it is seeing is above or below a threshold that would have been set. Okay. So that's your detection. For part of your processing, we talk about protection systems, but these that we have here are all relays. All right. So you have your differential system, which would be using a differential relay. You have a distance system, which again would use a distance relay, and your overcurrent protection system, which would be using an overcurrent relay. All right, so these are all relays, but related to or used as part of your differential systems, your distance systems, or your overcurrent systems. I know that for machines 2, you would have looked at differential protection for your 3-phase transformer. So we you know, tease you a little with that one in machines. You get some other fundamentals here, and then if you decide to cross over to protection, then we throw the entire shebang at you. All right. And then for isolation, we're talking about your breakers and your fuses. All right. And there are different technologies for your breakers. All right. And I believe by now JPS has removed all its oil circuit breakers. I can't, you know, let me not speak too much on that. But there was a program of removing them and replacing them with SF6 breakers. But the technologies for your breakers has been changing, has been evolving. And then of course your fuses. So we process using these relays, your protection systems, and then we isolate there. So we now come to what I referred to briefly earlier when I spoke about your protective gear. And your protective gear is simply that set of equipment that's used for detecting, locating, and initiating the removal of a fault from the power system. All right? So we talk about detecting. Locating would fall under processing. All right? So that would fall under processing. And then initiation in terms of isolation. So if we go back to the list I gave you earlier, you would see that detection, so we have CTs, VTs, etc., comes under detection. Processing would be different, the various relays, yes? And of course, the initiation, the only thing that is left out of the protective gear, right, is the isolation. So we have the initiation, which would come from the relays, because the relays will indicate what action needs to take place. So they will say whether or not we should be issuing an alarm or whether we should be isolating. So what I'm trying to say here is that your protective gear is everything outside of your circuit breakers. So we talk about protective gear, we're talking about all the equipment which is used as part of your protection system, with the exception of your circuit breakers. Your circuit breakers will be known as your switch gear. All right? So just giving you the list here, your protective gear would include all of this. So I'm glad I didn't mention this there, or your shunts, all right? All of this is part of your protective gear. For your
Good afternoon, sir.
Right.
I just have a good
Yes,
afternoon,
sir.
sir. I have a question. As it relates to the relays that you're talking about, could you give me like an idea of probably a pictorial view of that relay, or of the relay that you're talking about? Not literally, but I know you said the relay is supposed to monitor in terms of what state it should be given an alarm and all of that. But we just want to have an idea of that type
What
of relay.
relay look like?
Yes, sir. You can't, if you give me the name, but I can search for it, if not description or something.
I am actually looking to see if let me also look at something. Let me see if I have it in the presentation, because when we talk about what did I do? When we talk about the relays, you have I'm just looking to see if I have any in this presentation. Good. I have one here. So, are you seeing this?
Yes, I'm ready, sir.
Now you're seeing it. Are you seeing the screen?
No, sir,
No,
we're
sir.
seeing you and your
No,
cupboard.
sir, we're seeing, you're not sharing now.
Only
sir.
seeing me. Oh, sorry. Imagine that must be scary. All right. Let me add something to it. All right. You're seeing the screen now?
Yes, sir.
All right. So this is an example of a relay. This is an SCL. very popular at JPSCO. This is a static relay. Ah, come on. All right, a static relay. This meaning that it's using microprocessors. All right. What we have on the left here, your electromechanical. This is what. Okay, so let me. I'm trying to. Okay, the one on the left, I'm not able to read the writing on it, but I believe it is a overcurrent relay. All right. Now, that relay would be monitoring one phase of your power line, for example. Good. So for me to monitor an entire line, the 3 phases, I would need one of these on the left per phase. All right. Over here, this SCL relay will monitor all 3 phases. On top of that, you may be able to have more than one operation from it. So you may be able to get overcurrent as well as distance. So in other words, the relay technology has resulted in the relay house not being as large as it used to be. Well, I suppose the only drawback is that now you need air conditioning in your relay rooms. But yeah, so what you're looking at is a relay. All right? Or what you were looking at.
Thank you, sir.
All right, so let's go back now. Where are we? Okay, so this is where we are. Now, remember I said at the beginning that it's important that we isolate only the faulted section of the system and allow the unfaulted section to continue operating. So it needs to be, there needs to be discrimination. It needs to be done quickly. It needs to be applicable to different configurations, operating conditions, and construction features. Right? So in other words, whether I am looking at, I want to talk about configurations, whether I'm looking at a ring system, whether I'm looking at a radial system, whether I am looking at, let's say we're talking about your transformers, whether I'm looking at a delta, a star delta transformer, whether I'm looking at a star star, you name it. These are all the variations that will be part and parcel of your power system. And we must be able to protect that system with all these configurations, with all these variations. And we must be able to do it quickly and with a high level of discrimination. So in protection, or maybe I should put it this way, discrimination is acceptable, or is a highly acceptable principle in protection. That's one time you can discriminate and don't feel bad about it. Because, and what that means is that you should be able to separate the abnormal, the section of the system that is operating abnormally from the other section which is operating normally, and do so quickly. All right. So with that said, we can now look at some other definitions and some other aspects of your protection system that we need to be able to appreciate and understand. So let's start with what relays respond to. Remember I said earlier that with the generator, if the generator is vibrating too much, it means that there's a fault. If it's vibrating too much, it means that you may have a hairline fracture on the shaft. That is something that has happened here in Jamaica. All right, one of our independent power producers had the vibration going for a little while on its generator. I can't say whether or not it was ignored or they didn't understand what was happening, but you know, they kept operating and ended up losing the generator. So the system was down some 30 megawatts with that generator out. You have frequency diversions, but remember we said, again, coming back to power systems now, we want to have a reliable supply, yes, and at certain standards. So we must know that when we plug our equipment in, we're operating at 50 hertz, not 50.8, not 51, not 49.8 or 49.3, yes, but 50. It sounds like when you guys willing to round off and tell me that there's nothing wrong with it. But anyway, so 50 is 50, right? We have relays that respond to the magnitude of current. We have relays that respond to impedance. So, you know, a fault occurs on a power line and the relay actually measures the impedance from the relaying point to where the fault is. And based on that measurement, it will determine whether or not the fault is on the line itself or the fault is on an adjacent line. And of course, we have relays that will measure power, okay? So in terms of just making a quick distinction here, because I know I may have been using the terms interchangeably, but just let's make the distinction. For each individual arrangement in terms of protection. So if I'm protecting just a transformer, yes, and I'm using an overcurrent relay, that's a protection system. When that is now coordinated with other protection systems, then I'm talking about a scheme. All right. So the system represents the individual arrangements, and the scheme represents the coordinated or coordinated combination of relays. Because you don't want the wrong relay to operate. You don't want a fault to be on the kitchen circuit, but the circuit breaker for the living room trips. Yes? The appropriate relay must trip for the fault that is associated with its circuit. So we make the distinction between system and scheme. I think we have made this point already, so I can move on. All right, so some definitions now. And these definitions, are things that you may want to pay attention to. So we talk about reliability. If the protection system is reliable, it is speaking to its ability to operate when required. So remember I spoke earlier about the breaker and the fact that moisture could have been getting into the panel, the breaker could have corroded, etc., etc. Then when you have a fault, no operation, it means that would be unreliable. But the reliability of a protection system is that it will operate when required, even if it has not operated before. So how are you going to ensure that? You have to carry out things like routine maintenance. All right? So you have to maintain your breakers. You have to ensure that the breakers will operate when required. You can't wait until you have a fault, then you realize that the breaker, there was something wrong with the the operating coils on the breaker. All right. So reliability, operate when required.
I'm sorry.
Yes.
How you carry out maintenance on the breaker without disrupting the system?
You can do that, man. You bypass the breaker. You could do that?
What you mean by, sir? Is it that?
Yeah,
you're
man,
not
I'm
in-
good. I
because-
understand.
Huh?
Because earlier,
What
sir,
I mean by that, I mean you bypass it.
no, man, I know what you're saying.
In other
Because I'm
words,
talking-
well, let me answer it this way. You have a number of ways. And I come back to something simple, which is in your home. Let us say you wanted to, let's say a breaker went bad and you need to go and buy it, but the people at home still need power from that circuit. You have a couple options. You can either take that line and put it directly on the bus bar, you can take it and put it on another breaker. Obviously, it will not be a permanent solution, but you are replacing the breaker, but the people still have power.
Good, sir. What I mean,
Yeah, but sir, in between the system
human
that would be
intervention.
disrupted.
Huh?
That still would disrupt the circuit.
Yeah, but hold on, you have switching. Yeah, you have that up. That will happen. Yes. So you do have switching, what do you call it? No, some switching techniques that you use for your isolators, etc. But you're gonna lose power for a little while. But the fact is, the customer will not be staying out of power until you finish your servicing.
Yeah, that was what I meant, because I know there must be disruption, even for a short duration.
Minor disruption.
Sir,
Excuse me, 1 minute, sir. So what if you bridge it over before you take it out? It don't much of a disrupt.
I don't like them word there, I'm saying.
But George, we never do that. You kill yourself, man.
I kind of disagree with the disruption of the supply.
Yes, Mr. Clark?
I kind of disagree with the supply being disrupted.
As I said, there are some switching, what do you call it? There's a switching order that you can bypass the breaker before taking it out.
Okay. The next question.
All right. You see, this is a good discussion because maybe I can invigilate to the protection, because when we go into the substation, they'll be able to, do I have any? All right, maybe I have some pictures of the isolators. So I would show you where it goes above the breaker. So you can then make the switch and then remove the breaker. But go ahead, Mr. But I don't like the term that George used about bridging. Yes, Mr. Clark.
Yeah, all right. So in terms of the protection system that you're talking about, if you should bypass the breaker, wouldn't that leave a system, even for the period of time of maintenance, wouldn't that leave a system vulnerable
Yes.
for a fault in case there is one?
Yes.
So how would you go about?
So if there's a fault, what will happen is that instead of you having a small area being isolated, it means that the isolation will be greater. The area of isolation will be greater.
Okay. You also mentioned, even in a one-line diagram, we see where there is breakers that isolate, say, for example, a transformer. What if one of those breakers is out for maintenance? And
All right. All right. Mr. Clark, write down that question. And we are going to get to it. It is now, all right, it's 10 to 5. We're going to get to it in about half an hour. I'll explain that to you.
Okay.
In about half an hour. All right?
Okay, sir.
Okay. So, as I was saying, in terms of reliability, it's going to be impacted by the system design, installation, and deterioration. So I use the example of that breaker becoming corroded over time. Right? That's deterioration. So it means that maintenance needs to take place. All right. In terms of the installation, do we have this? All right, so we have design, installation, and deterioration. I'll just go into each of them now. So for your system design, yes. How the protection system that you put in place will be based on your understanding of the system that you're protecting. So if you don't understand the operation of a generator or a motor, you really are going to be at sea in terms of protecting it. All right. One classic protection system that we utilize is that of an earthing transformer. Now, where do I use this? Why do I use it? If you understand that for your generator, you're going to be earthing the windings, eh? You're going to be earthing your generator. So it's a star winding earth, right? Earth star. Which means that when you have the fault on any winding, an earth fault, you're going to get current through to your earth lead. That in of itself provides you an opportunity for protection. All right. So understanding the system, understanding the operation of the equipment. You guys have done machines too already? Let me do, trying to make sure.
Sorry, it is an elective.
Machines to
It's an elective.
One.
there's an
It's an
elective.
elective.
Okay. All right. So in machines 2, you're going to look at your star delta transformer. And in terms of the operation of that transformer, you have to think about the phase shift that's going to occur, that 30-degree phase shift. And as such, how you utilize, let's say, your differential protection is going to be dependent on you understanding that theory. Yes? A transformer, connect two systems of different voltages. You have to appreciate the fact that that is what a transformer does. And so in terms of the protection that you apply, it will have to take that into consideration. Yes? So system design, understanding the system is of critical importance for you to design a reliable protection system. The other area we mentioned is installation. Yes? Now, I don't know if any of you were at UTech when Mr. Ali taught there, but one of the stories he shared with me was this fellow who worked at Piarco Airport in Trinidad, was that he was responsible for, all the circuits, many of the lighting circuits at the airport. And every time they had a problem, they would call for this very handy fellow. And he would just go out, and in no time, the system will be fixed. And they're back to normal. Problem again, and he goes out and he fixes it. Then one day he left the job. And they suddenly realized that nobody understood anything about the system, because he structured it in such a way that only he could understand it. I suppose he was a smart man, he knew how to maintain his job. But the fact is, you do have systems that are overcomplicated, overcomplex, yes? That makes the system difficult to troubleshoot. Makes it difficult for you to maintain, basically. All right? So installation. Go ahead.
I was saying that is similar to Spanish Town Hospital. Just one person will understand everything about the electrical. And when you ask the other maintenance crew about it, they can't explain it. But that man is just very smart to maintain his job, as you have said a while ago.
It's unfortunate. It's an unfortunate place to be. And then deterioration comes back now to testing, you know, just doing your troubleshooting and carrying out your maintenance on the system, right? Simple maintenance activities like from time to time, I'm referring to it because since most of you would have been on campus, at least once you would have seen them washing insulators, washing the substation down at home. All right. Of course, you had bird droppings and that sort of thing, but that in of itself will impact the operation of the substation. So simple things like this. You have your transformers that you have to carry out maintenance on. You have for many of these transformers, you have a little pipe at the side of the transformer that you take some of the oil and test it. And based on the amount of sedimentation in the oil, then you know that there may be a fault on the transformer. And these faults, as I said earlier, are some that may require not isolation, but an alarm. Yeah, so you may have low oil in the transformer, which means that some of the windings may begin to be exposed. It doesn't require immediate or removal or discarding of the transformer. It just may mean that you may have a leak somewhere and you need to correct the leak and add back oil to the system. So you have to maintain a system. And you going out into the workforce will have to have that sense of the need for maintenance. All right. Let your manager tell you that he or she is taking a decision not to maintain, but never let it be that you are satisfied with not maintaining. All right. So we spoke about reliability. We now look at selectivity. And selectivity is the ability of the protection scheme to remove or isolate only the affected areas of the system. All right. Now, I've been using the term discrimination earlier, and we're just going to make a little, well, we'll explain a little further the difference between the two. So selectivity, to remove or isolate only the affected areas of the power system. And when we speak of selectivity, it is based on the type of protection system that we're talking about. And the two that we are mentioning here will be your time-graded systems and your unit systems. So selectivity, ability to select or to isolate only the affected systems of the power network. All right. So we just introduced these two here. For a time-graded system, the protection systems in successive zones are arranged to operate in times which are graded through the sequence of equipment. Now, on the surface, that don't mean a thing to you. Okay? All we're saying here, and it goes back to what Mr. Clark was asking earlier, in terms of how do we determine that one system operates ahead of the other? I think that's what you were saying, Mr. Clark. I hope I've gotten it correct. Your time-graded system. Yes, Mr. Is that what you were saying?
Yeah, something like that.
All right. So your time-graded system operates in a manner where the system or the primary system, the one that have primary responsibility for isolating or for protecting a particular section of the network, it is set such that it will operate faster, yes, than the rest of the system. If, however, it does not operate, then other breakers in the system will operate. And I think I have developed a fairly foolproof way of explaining this. So let's try this. So let's say a fire has broken out here. All right? So the fire is at, this is point 1, this is point 2, this is point 3. So the fire has broken out at point 3. The fire station that is responsible for putting out fires at point 3, that fire station is located at point 2. Now, how the protection system works in terms of a time-graded system is that it is expected that the fire truck will leave fire station 2 immediately after the fire starts. However, the fire chief at fire station 1 also dispatches a unit to the fire, to the same fire. What happens is that what happens, 1, it's either that the unit from 2 continues and extinguishes the fire, or for whatever reason, that does not happen. There's an accident, so it doesn't get to the fire. However, because Firehouse 1 had already dispatched a unit, it will continue, it will pass the accident and it go and extinguish the fire. That is how a time-graded system works. So what we're saying here is that when a fault occurs, a number of protective equipment will respond, which is why 1 also responds along with 2. So everybody responds. Only those relevant to the faulted zone, yes, will complete tripping. And what happens after that? The others make incomplete operations and reset. So if I go back to my fire example, if Firehouse 2 puts the fire out, then the guy at Firehouse 1 goes back home. Does my fire example work?
I'm just trying to process
Yes, sir.
how the
Makes
others
sense.
would respond, in what way they would respond.
Fire truck, man.
No, man, I'm talking about the time gradient system.
Remember the relays. Remember we spoke about, you have to go back to that four-step system that we spoke about. Detect, process, initiate. All right? So let's work with that, with what we have before us. If you have a fault, if you have a fault at UE, if you have a major fault at UE, every generator, however small, every generator on the island will detect that fault. All the breakers, well, let me not say the breakers, all the CTs would detect it. However, the primary CTs and associated breakers that should trip the fault at UE would be located at Hope. And I think Upper Camp. All right? But let us just keep it simple. Let's say it's at Hope. However, if for any reason Hope does not operate, the breaker at West King's house will operate. Why? Because Hope would see a larger current because it is closer to UE. So its breaker would operate faster because the relay would be seeing a larger current. But remember, I just said everybody would see the fault. But at West King's house, whilst it sees the fault, it would be seeing a smaller fault current, so it would be operating slower. With me, Mr.
Yes, sir. Yes, sir.
Operator?
That's much clearer.
Right?
Sorry.
So they are all operating, but the one that has primary responsibility would operate fastest. But if for whatever reason it does not complete the operation, those who would have also started the journey would continue the journey until they clear the fault. Yes, Mr. Wilby.
Sir, so you said that the other generators around the island would have detected the fault.
Yeah, man.
Is it that they will now be operating to or responding to that fault in any form or way?
All right. Now, I said all will detect it. The next question is the extent. What really would they be experiencing? You with me? So
Yes,
the fact that it is detected doesn't mean that the export of power to supply that fault would be significant for all.
So excuse me, so that would depend on the distance.
It would be dependent on proximity, yes.
Yeah.
Right? So they all detect it, but they do not all detect it at the same level. So for those that are closest, it will be more significant. So let me run through what happened in one of the more recent all-island blackouts that we had. There was a fault. There was some guys working on a line. I think it was down by on Spanish Town Road. Right? It was on Spanish Town Road. And when you're working on a line, you have a thing they call short and ground, right? That doesn't make sure it's the line dead when they're working on it. And there are certain protocols that should be followed. Meaning, the person who is going on the live line, he has a key, and they have this thing called lockout and tag out. Some of you who are in the industry, you may be familiar with those terms, right? For whatever reason, let me not say it that way, because I want the principle to come home so that you don't go there and carry that attitude, right? A man just feel lazy and he decides that, all right, yeah, man, you go and go do it, man. Long and short, the short and ground was not removed before they re-energized the line. So it should have been physically inspected by the supervisor, but he didn't. A man just say, yeah, man, me do it. Him say, all right, him call, you can re-energize the line. They re-energize. And so when they re-energized, what they did was to energize three-phase to ground fault. That's what they created. Right? So a solid fault, three-phase fault. Now, because it was a major line, the generators, I think it was a generator at Huntsby, tripped because it's this major load coming in. When that tripped, the power that was now being supplied to the southern part of the country, there was a significant shortfall. And now a significant amount of power needed to be supplied from Bogue. Now, Bogue can't supply that. So that trip also. And of course, the other generators say, well, since you all trip me gone to. I mean, it's not like that, but you get the picture, right?
Yes, sir.
And so everybody tripped. Why? Because a man was just too lazy to check for the short and ground and to clear it before energizing the line. Right?
All right, sir. One question, sir. In terms of protection, why wouldn't they have like in terms of an incident like that where it would like open and shed the load to keep those generators?
But we don't protect load. We don't protect load. We protect the system. The load is protected by the owner of the load.
I think he's saying so shed the load so that the generators could manage.
Yeah, but that's the point I'm making. That's what so in other words, what the system is doing is protecting itself.
Yeah, by tripping.
By tripping. So it removes the generation.
I think what he's referring to, sir, is just like when you have GPS sometime to time do load shedding.
But what I'm saying, Mr. Freighter, if you understand that, then you would ask the question. Remember, when we talked about load shedding, load shedding is about the company deliberately going in, yes, and shutting down, basically shutting down substations. That's basically what it is. Yes? That in of itself will take you, what, some minutes? Yes? When we are talking about a generator being removed from the system, we are talking about milliseconds. Get the difference now? So in protecting the system, you remove the generator because remember I said before, your generator is one of the most pampered piece of equipment in the power system.
Right, so
you can't afford to lose your generator. So you remove the generator from the system for its own protection. But the unfortunate, I think it would have been easier if you had done, well, let me not say it that way, but if we had looked at system stability and you understand the whole business of what happens when there's a loss of load or when there's a fault, then this would have been a lot easier for you to grasp. Yeah? But in terms of what happened, all right, that short circuit represented a significant overload to the system's generating capacity. And so the system just pulled away from it and the generators just went down like a set of dominoes. All right? And by the way, part of the reason it was so significant was that the fault occurred at about minutes to 6, which means that it was coming up to the peak. It was right at the peak. So once you start losing generation, it's just gonna be like a domino. All right. Okay, so the other option now, so we talk about time graded, you have unit systems, and I'm beyond the 40 minutes that I had promised Mr. Clark, but we're coming up, we're getting there. For your unit systems, these systems, excuse me, are designed to respond to faults within a clearly defined zone. And you can't use it right through the power system. It is heavily used. So when we talk about differential systems, those are unit systems. All right? Which means that if you have a differential system on a transformer and there's a fault on the transformer, the differential system will not be considering whatever else is happening on the network. It will simply remove the transformer from operating. No questions asked. Transformer, shut down. That's it. All right. We apply it to generators. We have voltage balance systems, differential. Yeah, we apply it to some types of lines, some lines. All right. But primarily, your differential would be applied to your transformers, your generators, etc. And as I said, they do not coordinate with any other part of the system, but operate once there's a fault on the equipment being protected. All right? And as a result, operation is extremely fast. Okay, so we now come to what we call zones of protection. All right, and this is where now I'll try to answer Mr. Clark's question. And when we talk about zones, it's really just the equipment and its associated breakup. So when we break up the system into zones, we're really looking at the protected equipment or the piece of equipment along with its switchgear. All right. So you have this system. I mean, the power system is in any country, is one of the largest piece of engineering, right? So in any country, your power system, largest piece of engineering, right? And you need to be protecting that. As a first step, you break it up into zones. So what does that look like? I hope you can see this. All right? So each of these little boxes here, those are your breakers. So for your transformer, those are your breakers. And where you see the dotted lines, those would represent your zones. So let me now speak to what Mr. Clark had asked. Let us consider this transformer, this generator, all right? And that generator is feeding into this bus. Okay? Yeah, Mr. Henry, and then we'll be.
This is what I was referring it to in terms of like zone, when we were talking about the blackout. Say you would have like protection to protect like a fault in one zone, to isolate that zone. So
Yeah,
but, don't come over.
Yeah, but remember what I said, you know, what was happening then is not that the zone didn't work. The zone did work. So you had the fault on the line, right? So, all right, let me try and use this figure and explain what happened.
All right, sir.
These are lines. So let us say I had a fault on this line, right? So this is where they had that solid three phase, right? Now that fault, let us say it's closest to this generator. And remember now, we're operating at peak. So all the generators are operating and pumping into the system. Because of the fault, this generator, seeing the significant increase in demand, it pulls out from the system. All right? Because it pulls out from the system, all of these other generators now became overloaded. Yeah? And because they were overloaded, I'm trying to go back to the first slide that we had. But remember, we're saying that in that whole power network, one of the issues that can impact your generator is overload. So if you ask the generator to go beyond its capacity, instead of doing so, which will be detrimental to its operation, it will pull out of synchronism. And if it pulls, obviously, if the generators pull out, the system collapses because there's no supply. So that is all that happened. But to Mr. Will be, you had a question also?
No, sir, it was from the last time. I didn't put it on.
Okay. All right. So back to what Mr. Clark was asking. So I'm going to use again this generator as reference. All right. If I have a fault on generator A, Mr. Clark, this breaker that I'm going to call A star is the breaker that should open in order to clear or to remove the generator from service. All right? If A star does not operate or doesn't operate quickly enough, then the following breakers are going to open. All of these that I have circled in blue would then open because the fault is no longer a generator fault, but it would be escalated to becoming a bus fault. Now, how do I know that it has escalated to become a bus fault? If you note all the breaker, if you note the dotted line around, the dotted area around the generator, that is the zone. But that zone overlaps with the zone for the bus bar. Remember what I said a zone is? Equipment plus breakers. So the equipment being protected here is the breaker. And the brake is the bus bar. And the breakers associated with that is this bus tie and all of these breakers. Yes, Mr. Johnson?
So these breakers that you just circled, these would be the breakers that are delayed. In other words, they wait and see if
A star operates.
Yeah, so these would be delayed.
Yes. All right, so the fault would move from being a generator fault to becoming a bus fault. Similarly, if I had a fault on this line, yes, the breakers that should operate would be these two. However, if, let's say this one operates and this one doesn't, this one doesn't operate, then these other two breakers will operate to remove the line. So if the fault is on the line and these two breakers operate, if those two operate, then you wouldn't even know that there was a fault. Because the line at the top, this one, would continue to connect bus A and bus B. So this line, the line at the bottom, would be isolated. It will be removed from the system because of the fault, but the customers would not know. We'll continue to operate. You with me? This is what discrimination is about.
So that line, sir,
Yes.
bus A, but we have bus A and bus B, wouldn't be overloaded.
Not
Or it is large enough to compensate for the loss of them.
That's a possibility.
Because if this line is going to be overloaded, then certainly the breaker is going to do everything to protect the line.
We understand that. We understand that. But if we can go by the lines that we have in Jamaica, many of our lines are operating at about 15% of their capacity. Right? Many of our lines are rated at 450 MVA, the transmission lines that we have here. So, you know, it's in this case, we would have an issue. All right? And many times when you see systems set up like this, it's what we refer to as redundancy. All right? So either or can run the system. Usually when you see parallel lines, yes, it's usually that you can run the system on the entire system on either of the two or both of them. All right? So, Mr. Clark, answer your question?
Yes, sir. You answer the question in terms of zone operation. But I want to ask the question now, sir. These breakers, do they function just like the one in our homes? Or
in terms of what?
In terms of the mechanism of how?
No.
Okay, so you're saying that these breakers actually use protection system as well, right?
No.
Relays and stuff like that.
Well, the breakers operate. Well, first of all, the breakers in our home, the fault current passes through those breakers and the or should I say the decision-making mechanism, the fault current passes through them, yes?
Mm-hmm.
In the power system, the decision-making mechanism does not carry the fault current. What it carries is a replica of the fault current. So the fault current passes through the lines, it passes through the CTs. Then the CTs take that information, sends it to the relay. The relay, based on the contacts that are used, and you know, you would be familiar with your normally closed and normally open contacts and all of that fanciness. It then energizing an operating arm on the breaker. Yes, so the fault current doesn't pass through the relay. So that contact then energizes the operating coil on the breaker, which then operates the breaker.
Okay, sir. So you're saying then that it don't necessarily mean that the breaker is defective or the mechanism is defective, but you're saying it could be why it don't operate is because of the relaying.
It could be many things. It could be many things. But what you as the person in charge need to ensure is that those many things are looked at where you need to run tests are tested and be in working order at all times. Yeah? The picture I showed you of the breaker, you would know that there is a port that the technicians from time to time would go in and download information from the breaker, from the relay in terms of its operations. Persons at system control, they are gathering information from these relays. So you have to be on your P's and Q's. I don't know if any of you have ever been down to system control. And if you are not careful, you will wonder what these guys are really doing, if they're really working. But it's a very, very critical part of the network. All right. All right. So what time is it? Oh. Oops. All right. So let's speed it up a little. Now we talk about stability. Yeah. So I mentioned unit systems earlier, but for stability, what we are talking about is the ability to remain non-responsive to all load and fall conditions outside of the zone. Yes, and this really focuses on unit systems, because time-dependent systems, you would not have this in place, because if it's time-dependent, it means that everybody would respond simultaneously, just that some respond slower than others. You with me? All right. So in the time-dependent systems, we refer to that as discrimination, which I mentioned before. And then stability now says, listen, don't operate if it doesn't concern you. So if I have a differential system protecting my transformer, and there's a fault on my line, the fault on the line has nothing to do with the transformer. So the differential on the transformer must ignore the fault. That's basically what we're saying. All right? So that's stability. Speed goes without saying. Yes? We want to be able to isolate as fast as possible. But while we operate as quickly as possible, we want to ensure that we do so accurately. Now, I refer here to loss of synchronism, which again goes back to, would have gone back to your understanding had we gone through it, of stability. Yes? Because loss of synchronism simply means that there is a challenge between the generation and the supply of power, or the load. So if you have a load generation mismatch, whether it is as a result of a fault, whether it is as a result of a loss of load. Because if you suddenly lose the load, if you think about how a generator operates, you have a prime mover. Yes? You have your turbine. And let us say it's a steam turbine. And you're driving all this steam, you have produced all this steam. And then suddenly, the load that you were supplying is lost. For whatever reason, there could be a fault out there and isolation takes place and the load is lost. Yes? The power that is coming in, the mechanical power that is being supplied to the turbine, which is transferred to the generator, you can't suddenly stop it. So electrical power can be lost in a matter of seconds. But the mechanical power, because of how that is produced, it's not so easy to stop that. So it means that the loss of load is going to cause your generator to overspeed. And if your generator detects that it is overspeeding, then it's going to just seek to be isolated also from the system. Right? Or if you have a significant fault out there the generator would have seen the significant increase in demand. And so the mechanical power, again, can't change as quickly to meet the increased demand, right? So we can't just suddenly increase the steam input or the mechanical input, whatever the input is, whatever mechanical force we're using to drive the generator. That can't increase suddenly. And so again, the possibility is that you're then gonna have your generator slowing down because the electrical load will be greater than the mechanical load. Loss of synchronism. And so you want to ensure that whatever protection mechanism you have put in place would operate as quickly as possible to prevent loss of synchronism. So you would want to remove that fault before the generator loses synchronism and pulls out of the system. And whilst we have not looked at it, you may hear the term, which would be known as the critical clearing time, meaning the maximum time that the fault can remain on the system before the generator loses synchronism. Yeah? All right. So speed, it's important, but it should not be sacrificed for correct operation. And whenever I say this, I go back to this cricketer Patrick Patterson, but then again, it has that story would have lost its relevance because you're all too young. You don't know Patterson. So I can move on.
I know him, sir. What about him, sir? Patrick Patterson.
I'm afraid you're not with me at your age show, man. Make we continue, man. We can't make them know. Let's move on. Sensitivity refers to the magnitude of primary current required to operate the system. Yes? And when we talk about individual relays, we measure that sensitivity in terms of the volt amperes. At minimum operating current. And when we talk about relays and volt amperes, that's referred to as the burden of the relay. We'll talk about that. We'll definitely talk about that. Next. Where are we now? So we're talking about primary and backup protection. It really depends on how important your circuit is. And as I said to students, when we talk about generators, for my generator at home, all I have is an earth rod. That's it. That's all the protection it's gonna get. All right. But of course, when we now expand to 40 megawatt generator, then we have to think of the possibility that the primary protection, which in many instances would have been your differential protection, that may fail. So you may want to back it up with overcurrent protection. Yes? You may also want to set up, depending on how important this generator is. Remember, gentlemen and ladies, the importance, it is better to remove the generator from service. Yes? So in other words, you're going to spend a lot on protection. So companies spend a lot of money on protection because it is much more expensive to replace equipment. All right? So you have primary protection, which is the protection you want to be using to remove the equipment during fault, but then the possibilities that that can fail. So you want to have supplemental protection, which we refer to as secondary, or you can have tertiary schemes, again, depending on how important the system or the equipment is. All right. So in terms of backup protection, well, we said that earlier, depending on how important, then you want to do that. So backup protection can be obtained as an inherent feature of the protection scheme. So a time-graded scheme, such as your overcurrent or your distance protection, inherently has backup. And so what I mentioned earlier in terms, remember that firehouse example, and the fact that we said that all the systems will detect the fault, all will start operating, but if the primary protection operates, then the others will simply retreat and reset. That type of operation is obtained when we are dealing with overcurrent or distance schemes. And remember, students, we are dealing with protection fundamentals. So I'm not getting into the details. If you want the details, see you in January, right? So your time-graded schemes, your overcurrent and your distance schemes, these have backup as an inherent part of their operation. When you deal with unit schemes like your differential, right? When you use unit schemes, you now have to deliberately put in backup schemes. So for your unit, you will not have automatic backup. And you have to then go in and put in additional backup. Right? And as would be expected, you want your backup to operate slower than your primary. Because if it operates faster than your primary, then it becomes the primary and the primary the backup, right? All right, so in terms of the definitions, we wrap up that. Let's see where we are. Wow. All right.
So sir, the backup will operate fast enough to take out the generator in the event if the primary fails.
Yeah, man. That's the idea, yes. But as I said, the details in how we achieve that, we're talking about in January. I have to allow you to spend some money to learn that part. Did I say that on tape?
Sir, almost so. It depends on how the semester goes, sir. Whether it depends on how power system goes for us to determine whether or not we cross over to
Mr. Frater, you need to go back to you need to go back to bribery school. They didn't teach you how to bribe, man. So
it's a young tweet, man.
Okay, so the next thing we want to quickly look at this afternoon, we have 10 minutes. We want to talk about power system transducers. All right. And the transducer, we all know what a transducer is. In power systems, we are talking here about your CTs and your VTs. That's your current transformers and your voltage transformers. So your transducers are used for coupling, measuring instruments and relays whenever the values of voltage or current are too high. Yeah? So for your CT, they're usually going to be using a CT when you have currents above 200 amperes. So when you start dealing with currents in that region, 200 and above, you start thinking about CTs. And note, your power system transducers are used for both measuring. So in terms of metering, you may need CTs because you can't put the 200 amperes through the meter. So you have CTs, and then the output of those CTs goes to the meter. All right. Then you also have your CTs going to your relays, and you know, as we said before, your relays help with the processing of the information and determine what happens. So your CTs, again, because you're now over your 200 amperes, you're not going to see 200 coming through the secondary. So all it is doing is scaling that current value and giving you an output. All right? The standard output, for example, for your VT, your voltage transformer, and by the way, just to make the distinction here, a quick comment here regarding VTs. If you have an older textbook, you might see it referred to as PTs, potential transformers. Same thing, but in the modern world, we call it VT. Your voltage transformers, the standard output is 110 volts face to face. All right? It's 110 volts. So, you know, well, this really has more relevance. But anyway, they're very expensive. So VTs are very expensive because you're talking about taking voltages from all the way of 69 kV, 138 kV, 765 kV, and you're bringing it down to 110. That is a whole heap of transformation. Because remember, in the substation, I'm using Jamaica as reference, in the substation, you're going from 138 to a minimum 24 kilovolts. Yes? Your PT is taking it from 138 to 110 volts. That's significant. So your PTs are usually very expensive and are very large. But the key here, they produce scale replica. So we may take the current from 1,000 amperes down to 5 amperes. Yeah? All right, I don't want to stress you with that. All right, so what we are saying here is that you all did networks too. You all did transients, eh? So you know what a transient is. So what we have here is that what we are saying here is that the transient, the time for the transient to die out, yes? Time for the transient to die out can be much longer than the time that we need to clear the fault. If you recall, we can either have the system being overdamped, critically damped, or underdamped. It's not that it is not damped when we talk about underdamped, it's just that it will continue to oscillate for a little while, even though the oscillations are being reduced in amplitude. Yeah? But the fact is, you know, whilst that is happening, the power system is burning. So there are certain errors that we have to take note of in our CTs and VTs. And these errors, all right? And I'm trying to remember if I gave you a table. Let me just, okay, well, all right. So there are errors that you have to take into consideration, and there are also standards or precision CTs, as we put them. And so if you're being called upon to purchase a CT for measurement, so this is another warning I'm giving you. You're required to get CTs that's going to provide measurement, meaning it's going to be used to dictate how much money you pay the utility. You have to ensure that you get measuring CTs, which have very low error values. So you can't use a protection CT for measurement purposes. Right? Either you go and get robbed or the company. And I guarantee you that the company is not going to get robbed. Right? So you want to select the appropriate CT for the operation that you are carrying out. Okay? So for your CT, you have the CT and VT, you have the primary connected. Oh, yeah, 3 minutes. You have the primary connected to the power system, and the secondary connected to the relay. All right, and we're just going to end with those, with the figures on those, and then next week we pick it up from here, look at some problems, and yeah, that should be it. So remember, this is supposed to be VT, right? That's VT. So for your VT, connected on the power line, and you're getting your 110. For your CT, it goes, the line runs through it, right? And you get your yes, Ms. Henry.
Sir, I would like to speak to you after class, sir.
Okay. So this would be you see, so these are your CTs, right? And these bus bars, so this would be in an industrial setting. These bus bars are running through your CTs, right? And then you are getting the output from them, doing whatever you're doing with them, whether for display or for measurement, you name it. Okay? So that is where I'm gonna end it for today. All right. This is your output curve for your CT. But what I will do, I will send a picture of this in Schoology. So you come next week and be able to make sense of what is there. I'll also send you information regarding your relay, yes, which will be used. We'll be using that for some calculations. All right, so let me just bring up everybody and just screenshot who is here. Let's see.
One of the relays, sir. You're gonna send anything for the breaker or just the relay we need it for?
Relay.
Okay, sir.
All right, let's see. Don't go yet. Don't go. Print screen. No. All right. Yeah, that's it. So have a good one. All things being equal, I see you on Tuesday.
Okay, sir.
All right, good.
Sir, can have a word with you, sir.
Sir, aren't you forgetting something?
Again?
Aren't you forgetting something, sir?
Me?
Yeah.
Yeah, I've gotten forgetful, but what am I forgetting? I don't know.
The register.
So no,
Money
you
take
don't
us.
listen.
What do I want to
No.
Sir, if we get registered,
Man, deep in the lesson, man.
Just wake up,
you know
man.
that. That's just interesting. Just to know. You know, say everybody their class.
Just wake up.
Well, that means you weren't listening either, because I did take the register.
Well, all right, sir.
In screenshot, in screenshot. Sir, up to power technology.
Yes, sir. Upgrade, upgrade.
Okay, sir.
All right, take it easy.
Okay, take care.
Sir, can I go ahead now, sir?
Yeah, man.
All right, in terms of the interim report that is due
Sir, still recording.
Thanks.